this? I say that. Kind of was dependent on that. There it is. Haha, success. All right, cool. So we're talking about kinetics of a reaction now, right? And that revolves around the rate of a reaction. How quickly is a reaction proceeding? And so what we ended with last time was talking about this concept of rate order, okay? So if we just kind of look at this equation right here, what this is saying is that the rate of a reaction is proportional to the concentration of reactant, right? So it depends on how much reactant you have in there. And it's proportional in such a way that it's the concentration of that reactant times some constant K. We don't know what that rate constant is. It's going to be specific to each reaction. But then interestingly raised to the power of n. And n is what we called the rate order. There's no way to know what the rate order is just by looking at a balanced chemical equation. It's something that you have to do by looking at data. Okay? But out of all the reactions that they've analyzed, it turns out that like 99% of them fall into this bucket where n is one of three values, either 0, 1, or 2. So all the reactions we're going to study are going to have those sort of rate orders of either being 0, 1, or 2. And this is what we call the order of the reaction. So if n equals 0, it's a 0-order reaction. If n equals 1, it's a first-order reaction. And if n equals 2, it's a second-order reaction. Right? So what our goal was last class was to take some data of initial rates of a reaction against the concentrations of reactant. And we took this data and we analyzed it to determine the rate of the reaction, or the rate order of the reaction. Right? So the way that we did that was by taking the ratio of two of those data points. We used that same expression that we just looked at, K equals the concentration of A to the power of N. We took that for these two rates, so then we stacked them on top of each other. That allowed us to cancel out that rate constant K, because it's a constant. It's in both of them, so I get to cancel it. All right? So then I just plugged in my values for my data here, right? So let's just take a look, make sure we can see where we're getting this. Right, so here was the rate of data point 2. Here was the rate of data point 1. Here was the concentration of data point 2. Here was the concentration of data point 1. All right, so I just plugged in that data that I had. And now the only thing that's missing, that only variable, is n. So I can simplify those ratios. That would give me 4 equals 2 to the n. Okay, and then one of the ways that we can sort of solve for this exponent, so first of all, you can start plugging in values, 0, 1, or 2, and you can figure out what 2 to the power of what is 4, right? So that's one way to do it. If we're going to be good with our algebra, what we can do is take advantage of these log functions. If we take the log of both sides, that allows us to pull out that 2. So then the ratio of those logs is how we solve for that value of n. All right, that's what we did last time. Whoa. So now we're going to talk about a little more complicated reactions. This was specifically for what's called, a unimolecular reaction where we just have one reactant going to product, right? A lot of reactions don't just involve one single reactant. So now we're going to look at a bimolecular reaction, right? So now A plus B goes to product. And we're going to ask ourselves what the rate expression for this reaction is. All right? So it's going to be that same, it's going to look very similar. We're going to have that rate constant K, and it's going to depend on the concentration of my reactants. So it's going to depend on the concentration of A raised to some power, right? The order that it is. And then it's also going to depend on the concentration of B. So now that I have a second reactant in there, I'm going to have this second reactant in my rate expression as well. And we're going to raise that to some power, n. So that exponent m We call that the rate order with respect to A. And for N, we call that the rate order with respect to B. Right? Because they're their exponents. Importantly, we also have this term for the value that you get when you sum up M and N. Right? So if I take those two exponents and I add them up, we call this the overall reaction order. Right, so now we've just sort of expanded this idea of our rate expression to include yet another reactant, right? So previously, we were only dealing with these unimolecular reactions, things with one reactant. Now we're talking about these bimolecular reactions, things with two reactants, right? So we just kind of extended this concept. But now, again, we can't tell what these rate orders are just by looking at a chemical equation, so we're going to have to look at some data and figure it out. All right, so let's take a look at a data set here. So this is this specific reaction that we're going to be looking at. The reaction, if you take nitrogen dioxide and carbon monoxide, and you put them together to create nitrogen monoxide and carbon dioxide. So that's our reaction. And we have this initial rate data, again, similar to what we had before, where we have the concentration of each reactant as well as the initial rate of the reaction once we mix those together, right? So I'm going to take 0.1 molar nitrogen dioxide and 0.1 molar carbon monoxide and throw them together and measure the rate of the reaction. Okay, so now we need to analyze this to figure, whoa, don't do that, to get our rate orders. So again, the rate is equal to K times the concentration of A to the M and B to the N, right? And just to be clear, whoops, this is what I'm solving for. I'm trying to find those rate orders, right? Those exponents. Now it's going to be a little bit more complicated because I have both of these reactants in here. Okay, so how am I going to do this? The real strategy here, the important bit, is you just have to be very strategic as to which data points you pick. Previously, we said you could pick any two data points and stack them on top of each other, and you can figure out the rate order that way. If we have multiple reactants, we're going to be able to play a similar game. We just have to be more strategic about the points that we pick. All right, so I'm going to label these points 1, 2, 3, and 4. And in order to determine M, the rate order with respect to A, I'm going to pick these first two data points here. All right, and let me tell you why I picked those first two data points. Because in those first two data points, I can see that the concentration of A, the concentration of that first reactant is changing. But very importantly, the concentration of my second reactant is being held constant. So that's what we're looking for in the data points that we choose. One thing's changing, the other thing's held constant. If both of them are changing, it's chaos. I can't figure it out that way, right? So I need one of them to be held constant in order to figure this out. All right, and I guess I can be more specific here. Instead of saying A and B, let's say we can just put in the concentration of our specific reactants here. Cool. All right, so I'm going to play the same game that I played before, where I'm going to take the ratio of these two data points, right? So the rate of data point 2 over the rate of data point 1, that's what I'm going to do. And now I'm going to use this expression that I have for my rates, right? So on the other side is going to go the K to the concentration of nitrogen dioxide in the second data point to the power of M times the concentration of carbon monoxide in the second data point to the power of n divided by K, same idea, but now I'm looking at the first data point for each of these reactants. So to be clear, these are my data points that I'm looking at. At the top, I'm taking that second data point. At the bottom, I'm looking at that first data point. All right, that's what I mean by those subscripts. You could have flipped it upside down and gotten the same answer. It doesn't really matter. All right, if we stack the bigger number on the smaller number, it makes our math a little easier sometimes, but it's not impossible to do it the other way. All right, so now actually before we even get going here plugging in numbers, let's ask ourselves, what can I cancel out from this expression on the right-hand side? Okay, so I can cancel out that equilibrium constant because it's a constant. But because I was really smart in picking my data points, and I picked data points for which this carbon monoxide concentration is not changing, what else do I get to cross out? The concentration of the carbon monoxide. This term also cancels out, right? That's why I got to be really smart with the data points I pick. As long as I am, it simplifies this process greatly. So now I can just plug in my numbers. The rate of the second data point divided by the rate of the first data point equals the concentration of the nitrogen dioxide to the power of m. And my, oh, I've switched it up. Whoops. Over the concentration at my first data point. All right, importantly, how exponents work, this bottom term here I can simplify to 0.20 divided by 0.10, all to the power of m. Okay, so I want you all to take a second and see if you can't, based on what we did last time, right? You're just applying the exact same process. Figure out what the order of this reaction is. Try to solve this for m for me, and then we'll walk through it. And I will just caution, this is like real data, so the numbers aren't going to work out to be perfect whole numbers like they did last time. There's going to be some error in here. Nonetheless, you can sort of just round it up and you'll be able to see very easily what the rate will be. All right, before we had like perfect data that worked out to be perfect whole numbers. It's a little bit messier with real data. Say it again? Yes, it will. Yep, exactly. All right, so now I'm just going to punch into my calculator and take these ratios here. So this value on my left-hand side is 3.90476. I'm just going to copy a bunch of numbers. And then 0.2 divided by 0.1 is exactly 2 to the power of m. All right, so m is what I'm solving for. So again, I can take advantage of that log algebra. I know log algebra is really weird. You kind of either know it or you don't. It's kind of a different sort of way of organizing stuff. I always had a math teacher that said, like, in the magical world of logarithms, like taking an exponent becomes multiplication. There's all these weird rules that are kind of counterintuitive. Regardless, one of them is that if I take the log of 2 to the m, this is the same thing as m times the log of 2. All All right, and if you don't remember that from algebra class, I guess, you can just trust me on it. All right, but I got to take if I'm going to do something to one side, I got to do it to both sides, right? So I'm going to take the log over here as well. And now, because I have this m value pulled out, I can then just take the ratio of those two, divide both sides by the log of 2, rather, and that will give me that value of m is 1.965. And so again, this is real data, so it doesn't work out to be a nice, neat whole number, but nonetheless, we can tell that this is a reaction with an order of 2. Okay? And importantly, it's 2 with an order of 2 with respect to nitrogen dioxide, right? I've only solved half of this rate expression here. Okay, so what I'm going to actually do is plug in, I'm going to kind of change this equation here now that we know m. I'm going to go ahead and replace that with that 2. Okay, so now I'm going to clear the board here. Okay. And now we're going to try to find out the order with respect to N. We want with respect to B, our second reactant, the carbon monoxide, right? So we're trying to find the value of N. All right, that's the only thing we're missing order-wise from our rate expression here. So looking at our data points, I want everybody to take a minute and see if you can't tell me which 2 data points we're going to choose in order to determine the order of this reaction with respect to carbon monoxide, our second reactant. 2 and 3. Why 2 and 3? Because the other reactant, the one that I don't care about now, which is the NO2, is held constant. Perfect. That means it'll cross out of my rate expression when I take the ratio. And importantly, the carbon monoxide concentration is changing. So we can repeat this exact same process here, but if we're really smart and we remember something that we learned last time, just by looking at this data here, all right, if we're going for the speed record, what is the order of this step? 0. Why is it 0? Because the rate's not changing, right? Despite the fact that the carbon monoxide concentration is changing, my rate is not changing at all, meaning it must be independent of that carbon monoxide concentration. Right? So this term here it can't be there because it's clearly not dependent on that concentration at all. Right? So the only way that that would make sense is if n was a value of 0. And you could absolutely just do it the long way and take the ratio of the rates. But again, going for the speed record, trying to save some time, one of the things that we can spy, 0 order reactions are very easy to spy because the rate will not change even though the concentration is changing. Okay, so that means that we're going to replace this with a 0, which of course anything raised to the power of 0 is just 1. So this kind of drops out altogether. So my overall rate expression, I'm going to make some room here. My overall rate expression simplifies such that the rate is equal to K times the concentration of nitrogen dioxide squared. Right, again, we had like the shell of our rate expression, and our goal was to get in there and actually find what the order is. Right? We had to look at some real data to figure out what the order of that rate was. All right, so let me clear these off. Okay, now that we have our order of our rate expression, now the only thing that's missing is K, the rate constant. So you're going to take a minute and solve for the rate constant of K, of this reaction right now. Okay, we got all the data that we need up on the screen in order to do it. So just think about what variables in that equation you have and which one you're missing. All right, importantly, we're missing K. That's what we're going to rearrange to solve for. Everything else you got up there. All right, so take a second and see if you can't get me that K value. All right, so let's just look at our expression. And we can just ask ourselves in our data table, do we have a concentration of nitrogen dioxide anywhere? Yes. Do we have a rate anywhere? Yeah, we got that in this column here, right? So we have both of those there. The logical question is like, okay, well then which freaking data point do I choose? Doesn't matter. They should all point to that same value. And because this is real data, there is a little bit of variation depending on which point you choose. But rounded to the correct number of sig figs, you would always get that same value. Okay? So in the real world, what you would do is like analyze each data point and then average them together or whatever. For our purposes, for not trying to take forever to answer a simple problem, we'll just pick one. Pick one and roll with it, right? You'll get the same value as long as you rounded the correct number of sig figs. So I'm just going to pick that first one because it's right there. So 0.0021 was the rate. The K is what I don't know. And then that concentration at that point was the 0.10 for my nitrogen dioxide. So I'm just going to take that and square it, remember, because it was raised to the power of 2 in my expression. Rearrange by dividing both sides by that 0.1 squared. And what I would find is that K is equal to 0.21. Right? And so we could, from this data here, not only could we determine the order of our reaction, but once we got that figured out, we can go as far as to actually determine what that rate constant for our reaction is as well. All right? So we can fill in our whole rate expression with this data here, this initial rate data. Okay? Right? So we got this value of K, but what are the units associated with this rate constant here? And it turns out that it's not just always the same unit, right? So it's not like molarity where it's moles per liter and it's always moles per liter for molarity. For here, it's going to depend on your actual rate expression. All right, so what we're going to do is we're going to take this rate expression and we're going to figure out what the units of K are. That's our goal here. Okay, so what I do know are the units of these other two components. These brackets, this concentration, what was that measured in? And we can even cheat and look back. Molarity, right? That's what we measure concentration in. Right, so I know that this term here is in units of molarity. I don't know what K is, though. And a rate is the change in concentration over time, right? So those units would be molarity per second. The entire purpose of K is to square off our units, right? My units on this side combined have to match my units on this side. So everybody take a second and see if you can't tell what the units of K are going to be in order to marry them on the right-hand side of this reaction. All right, so unit square as well, right? So if I got that inside of that square, I'm going to have m squared times k equals meters over seconds, right? So what times m squared would give me this, right? I can move m over, or rather m squared over. And what I'm going to find is that k is going to have to be in units of 1 over molarity per second. Right? That's the way that I'm going to square off those units. And again, it would change if the order of my reaction was different. Right? So we got to look at the unit. We got to look at our specific rate expression to figure out what the units of k are. The other way that you'll see this exact same thing written is m to the negative 1, s to the negative 1. That's the same thing. Okay, and again, this is just algebra here, but just to kind of remind us, x to the negative 2, that's the same thing as 1 over x squared. In fact, x to the negative anything is the same as 1 over x to that power, right? So that's where those units come from. Cool. All right. So using this data here, we were able to figure out our rate expression, and we were even able to go as far as to figure out k, and we actually know now that the units of k is this 1 over molar per second, 1 over molar second. Cool. All right. So the next thing we're going to talk about is what's called the integrated rate laws. Okay. We're going to go back to our simple unimolecular reaction here, where you just have one reactant A being converted to product. And by an integrated rate law, what do we mean? We mean that we're going to get this function of how the concentration of our reactant changes over time. That's what we're looking for, right? Concentration as a function of time. All right, so for our zero order reaction, we said that the rate was equal to just K, right? Because that taking the concentration of A to the power of 0 is 1, so that term dropped out. So all that rate is equal to that single value K, our rate constant. Now, if we remember when we if we sort of do our expression for A, this was the change in the concentration of A over the change in time, right? That was one of the first things that we talked about, was given a chemical equation, how can we sort of like get our expression to measure how concentration changes over time and get our rate value? And importantly, because A was a reactant, we have to take it and multiply it by -1, right? Because rates are always positive and the reactant concentration is decreasing. So in order to make it a positive value, I got to take that delta A over delta T and multiply it by -1. And so this is equal to the K. Now, this is called the integrated rate law because what we're going to do is take this and do some calculus on it. We're going to integrate it, right? So in the world of calculus, this delta expression would be d concentration of A over dt. Okay, so this is equal to K. And then I can integrate both sides with respect, whoops, wrong tool, with respect to time. And that's how I can get A as a function of time, right? The concentration of A as a function of time. Now, this is not a calculus class. And so if y'all want to, go ahead and derive this expression at, your party that you're going to tonight to impress your friends, because I know this topic comes up a lot, have at it. But this is not a calculus class. I'm not going to go through the ins and outs of taking an integral, so you can just trust me that this is what you'd get if you integrate both sides of this reaction, right? Again, what we're going to get is the concentration of A as a function of time. That was our goal. And for a zero order reaction, you integrate this side here. You'd actually have to move the negative sign over, but you get negative KT. Remember, when you integrate, it's always like plus constant. And in this case, that constant value is the initial concentration of A. All right? So this is our integrated rate law for the for our zero order reactions, right? The concentration of A as it's changing with time. All right, so now we're going to do the same thing, but for our first order reaction, this is the rate is equal to K, but now times that concentration of A. All right, that was our first order rate law. To be clear, just, how am I getting these, right? It's because we had this generalized expression, rate equals K times A to the power of its order. So all I'm doing is plugging in 0 for that order. That's how I got this expression here. Now I'm plugging in 1 into that expression. That's how I get this thing here. All right, just to be clear how I'm getting these. And now again, we're going to play the same game where we're going to integrate both sides with respect to t. Again, you can do it on your own or just kind of trust me about this. But what we're going to get here is that the concentration of A changes as a function of time. When you integrate this, because this side is also dependent on time, you have to use that special number E. You would have probably been introduced to E in your calculus class first. Bottom line is it's this special number, kind of like pi. You always use the symbol, though, because it's got a bunch of decimal points on it. All right, so again, this is the initial concentration of A times E to the power of negative KT. Okay, so this is our integrated rate law for the first order reactions. All right, now I'm going to take this expression here and plug in a 2 for n.
All right, so then the integrated rate law we get for these second order reactions is the concentration of A as a function of time is equal to that initial concentration of A divided by the initial concentration of A times K times T plus 1. Right, so here is this function that tells me how the concentration of A changes over time for a second order reaction, right? So these are our integrated rate laws. I just took that rate equation for each one and integrated it with respect to time, and that's how I got this function of how A changes over time. Okay, and these aren't, again, this isn't a calculus class, so these aren't things that you need to be able to do, from a calculus standpoint. You will have these functions on your constants page, but you need to know when it's appropriate to use them versus, say, the rate equation. All right, and so let's sort of illustrate how we can use this function here for our second order rate, second order reactions rather. So let's put down this equation here, and we're going to do it for the second order one, right? Because that's what we just did a bunch of work to figure out for this particular reaction. So we have this particular reaction, copy that over. And using the data for this reaction, we figured out what that rate law was, right? We figured out that this was indeed a second order reaction. So that's why we're going to use this rate expression here, or rather this integrated rate law for a second order reaction. And we even went as far as to figure out that not only was it a second order reaction, but also the value of K we found for this. Okay. And we're going to need an initial concentration of our of our reactant as well. And so we're going to let's just use this first data point here, okay, where the concentration of the nitrogen dioxide is that 0.10 molar. So concentration of A initially is 0.10 molar. So then we can take this equation and solve for the concentration of A. In this case, we can even explicitly say what we're talking about is this nitrogen dioxide as it changes over time, right? So first of all, at T equals 0, what should be the concentration of the nitrogen dioxide? Well, it should be that initial concentration, right? And you can convince yourselves of that by plugging a 0 in to our expression here. I can actually just move this down so that we have 0.10. All right, and so let's solve it for some other time points here, right? Because this is the whole shtick of what this function's doing for us, is it allows us to predict how the concentration of A is changing over time for this second order reaction right here. So let's see what the concentration will be after 5 seconds of this reaction, right? So for my equation, I'm going to plug in my initial concentration divided by that initial concentration times the K for this reaction is that 0.21 times my specific time point here, which we're going to say is 5 seconds, plus 1. Calculator. Oh. There we go. All right, and so we see at 5 seconds now the concentration has decreased to 0.0904977, whatever. All right, so now let's pick another time point. Let's do it for 10 seconds. Okay, so then I'm just going to take this equation here, and again, I'm going to plug in my initial concentration of A. I'm going to use my value for K. And now I'm going to use the time point, 10 seconds in for T. So same thing, but instead of 5, we're going to do 10. And we get 0.08264446. And we can see that this concentration is indeed decreasing. That's what we would expect, given that the A is being consumed in this reaction, right? So we could just keep on going, picking multiple time points, right? So what I've done is I've done exactly this, but I've done it in Excel, so I could do a bunch of time points and then take a plot afterwards. All right. And so this is what we get. We can see, so first of all, we're going to pay attention only to this column right here for right now. I'll explain what the rest of it is here in a second. But here we have the time. I guess I should have been good and labeled this column. This is time in seconds, right? So we said at T equals 0, my concentration is that 0.1, that initial concentration of A. We did the 5 time point as well, 5 seconds. That was the value that we got. And we did it at 10 seconds. That was the value that we got, right? So then I just took this and I did it at all of these time points here, calculating that, using that equation to calculate the concentration of A at all of those time points. And that's what I get here in orange. This is the concentration of A as it decreases over time for that second order reaction. All right. And then I did the same thing, but for a first order reaction. So just to compare how a first order and second order reaction looks, right? So first order is that A naught times E to the negative KT. So what I did was use the same initial value for A and the same value for K as I did for my second order reaction, but plug that into the equation for my first order reaction, calculating it at all these different time points. And that's how I got this blue curve here. All right, and so you can see that the concentration of A changes much more dramatically on that blue curve over time than it does on the orange curve, right? And that's what we had said previously. This isn't surprising because we had talked about how second order reactions are much more sensitive to the concentration of K. So when the concentration of A starts to decrease in a second order reaction, the rate starts to decrease really quickly. Compared to a first order reaction, which is still sensitive to the concentration of A, but not as much. And if we were to do a 0th order reaction, we could do that as well. We would see that that's even faster. It would be something like this. It's over real quick. If we use that same initial concentration and same value for K, because these are independent of the concentration of A.